We can
So,
start
hello
now.
everyone. Yes, we are going to start now. So, hello everyone, and good evening, good morning at some places, or good noon. So, we are here with our great speaker today. He is Imre Baraway, and he is from Rényi Mathematical Institute of Hungary Academy of Sciences. He is also appointed University College London, and his area of research is combinatorics and discrete geometry. Moreover, there are a lot of things about him, and there are a lot of things like mathematical prizes. He has won this mathematical prizes, which is now known as Paul Ardosh Prize. He is also one of the invited speaker in the International Congress of Mathematicians in Beijing. And furthermore, he is member of a Hungarian Academy of Sciences since 2016. Moreover, he is fellow of American Mathematical Society and Academia Europaea. He is chief editor in the editorial board and the editor of many journals as well. And he has a lot of publications and with a lot of notable results. So over to you, Dr. Imre Baraway. And today he is talking about vector sums theorems, their relatives and their applications. And thank you so much for accepting our invitation. It's really nice to have you being here in this talk.
Thank you for your kind words. May I start now?
Yes, sure.
So the topic is vector sum theorems, their relations and applications, and I tell you what vector sum theorem is. So V is a finite subset of vectors in d-dimensional space. All of them belong to the unit ball B of some norm. And the only condition is that the sum of the vectors, besides that, the sum of the vectors is 0. So if you imagine this is that you start out from this point, say, this point and one vector, another vector, another vector, another vector, another vector, it can go far away and it comes back here. Are you with me? And
yes, we are.
And the question is whether you can rearrange these vectors in such a way that all partial sums along this reordering are small. So what is written here, the sum of the vectors from 1 to k in this ordering has norm smaller than or equal to m for every single vector k. So every partial sum is small. And m is a constant independent of v, independent of what so independent of the particular set v that is given to you. Is just it's just a universal constant. So this is the question, and I will come back in a moment to the case how this question came about. But first, I want to tell you the case d equals 1, dimension 1. So there you have real numbers between 0, -1 and 1, right? And their sum is 0. And I want to show that you can rearrange them so that each partial sum is smaller than 1 in absolute value. And what you do is you start out with the positive elements and add them one by one to each other up to the point when you would cross with the next one +1. And when you would cross +1, you would choose negative numbers instead, and you go back one by one to the point when you would cross -1 if you choose the next negative one. So at that point, you start choosing positive ones again, etc. And you walk up and down on the interval -1, 1. So the case d equals 1 is very simple. And now I give you a proof of the statement for the Euclidean norm. This is a correct proof, but not such a good proof because I will present you a much better proof. But let's see this classical proof that is written here. So it will give you an exponential function of d for this bound. And the proof starts with choosing a subset W. It's here, subset W, so that the sum of the vectors in W has maximal norm among all subsets of the set V, of the subset V. And let the sum of these vectors be A. So the picture is here from 0 to A. This is the farthest point. Then from 0 to minus A, you get the complement, the sum of the complementary vectors is just minus A. So this is what you have. And what you also have is that there is an orthogonal plane here, orthogonal to A, which is passing through the origin. And this plane is nothing else but the d-1 dimensional Euclidean plane. And there is one thing that you have to check, namely that every vector which is in W has a positive scalar product with A. So this is very simple. If it had a negative scalar product with V, then I could add it to this minus A here, and then I would get a vector farther away from the origin than A. But you can check it by yourself because this is very simple. So assume that this is indeed the case. The vectors in W have positive scalar product with A, and the vectors not in W have negative scalar product with A. And let's see what we have next. We can project everything down onto this, every vector down onto this plane, H, and this is what you get. First of all, the projected vectors belong to the unit ball, Euclidean unit ball of the d-1 dimensional space, right? Because they had length shorter than 1, and then the projection is even shorter than 1. And the sum of the vectors in this bunch is exactly A, because this was the... so if I project them back to the plane, then I get a new set W star, which is the projection of these vectors, and the sum of the vectors in W star is 0, because they go up to A. So this, by induction, this gives you an ordering of W star with bound MD-1. Are you with me still? Can't hear any reaction.
Yes. Is there any question from the audience so far?
Well,
you can put your question in the chat box. Yes, there is no question so far. Please go ahead.
So I continue. So then you can apply the same method here with the vectors in V minus W, and you get an ordering of the vectors in V minus W star with the same bound MD-1. So what you have is you have the positive vectors go up to A, but all of them lie in a tube of radius MD-1. And the negative vectors also go down here in a spiral and go to minus A, and they also lie in the same tube. Now you use the one-dimensional version, so you start going up with the vectors until you would hit the hyperplane 1 above my plane H, and when you would hit it, you would choose negative vectors, and then you go down, and if you would cross the hyperplane at level -1, you would start choosing the other vectors, and this is an interlacing them all together. What you see is that MD star is smaller than or equal to 4MD star, MD-1 squared plus 1, which gives you this quantity over here. So this is a good proof which gives you an exponential bound. Any question about that? Apparently no question, so I continue with with the next one, I want to give another proof. A proof which gives a much stronger result, as you will see in a moment. And the good proof is going to use Kara-Theodoris theorem. Now, I hope everybody knows what Kara-Theodoris theorem from 1904 or 1911 is, but I repeat it no matter what. So A is a subset in the d-dimensional space, and A belongs to, the point A belongs to the convex hull of this set A. Then there is a subset B of A, such of size atmos d plus 1, so that A is contained in the convex hull of B. So here is a picture. The point A is in the convex hull of the set A, which is this polygon. And the statement is that there is a triangle whose vertices belong to the set A, which contains A. And in the picture you can see this is such a triangle. This triangle is a triangle containing A in its interior. So this is the theorem that I'm going to use, and now I start the proof. Proof will give m smaller than or equal to 1.5 times dimension. And it will work for every single norm, not only for the Euclidean norm, but for every single norm. And what I'm going to do, I construct a linear dependence, alpha sub I, from the set of vectors V to the numbers 0, 1, to the interval 0, 1, with the condition that some of the vectors with these coefficients, alpha I V times V, sum is 0. So this is a linear dependence of the vectors in V. And I put some extra conditions on these linear dependencies, namely, I write AI for the set of vectors in V on which alpha I is equal to 1. And I call D sub I the set of vectors on V for which alpha I is between 0, strictly between 0 and 1. Are you with me with that one? So this is the picture. Here is this is my general picture. Here is my set V. This is my set V going on. This is the 0, 1 interval. And this is the function alpha I. This is alpha I equals 1. This is alpha I between 0 and 1. And this alpha I equals 0. So this is the picture that you have to have in mind about this linear dependence. Instead of writing out this linear dependence like sum of alpha I V I equals V, I just consider this picture. And the statement is that AI plus 1 is always larger than strictly contains AI, but the difference between the two is not too big, smaller than or equal to D. And also the guys that are the vectors, the number of vectors for which alpha is between 0 and 1, strictly between 0 and 1, is small, atmos dimension. So this is what I'm going to construct. And this construction is going by induction on I. So this is what I'm going to do, and here is the case I equals 1, I have to construct alpha 1. Very good. So 0 is in the convex hull of V, right? Because the sum of the vectors is 0. So if I divide this linear dependence by the number of vectors n in the set, then I get a convex combination. So 0 is in the convex combination of is in the convex hull of V. So by Kara-Theodoris theorem, there is a subset V1 of size atmos d plus 1, so that the origin belongs to the convex hull of V1. Very good. So I have a linear dependence. This is my linear dependence here. Let me use another color. This is a linear dependence. This is V1 here. Another color, sorry. This is the linear dependence. This is between 0 and 1, and this is all 0 here. The size of this set is atmos d plus 1. So I can multiply this linear dependence with a positive constant so that the maximal element in this linear dependence is equal to 1. Then I get a new linear dependence. This is 1 here, at least on one element. This is between 0 and 1 on the remaining elements of V1 at most D element, and 0 outside. So this is the first step of the induction, and here is the second. Are you happy with the first step of the induction? Any question?
Yes, I
Good.
think so.
Then I move from the case alpha I to alpha I plus 1. So here is my alpha I. This alpha I is this function here. This function here. This is A sub I, this is D sub I. And then I understand that there is a linear dependence, namely, which is 0 here, 1 here, and on this part 1 minus alpha. So so which means that V minus AI, this set of vectors, contains the origin in the convex hull, right? Because the sum of the vectors with these coefficients is 0, so the origin is contained in the convex hull. This is written out here exceptionally. V in V1 minus alpha I V is 0 because of the sum of the vectors is 0. So this is a linear dependence. 0 belongs to the convex hull of this set because it is 0 here. The current territory, there is the set U, which is written here, of size at most D plus 1, so that the origin is in the convex hull of U. So which means there is a function beta, there is a linear dependence beta, which is positive only on U and 0 outside. And what I do now is I take alpha I and add T times beta to this alpha I, and I get I choose T a positive number so that another 1 appears. I choose it so big that a new 1 appears in the linear dependence. So what I have here is this is the old AI. This is a new element which became 1, and then there are some coefficients between 0 and 1. I don't know how many, but certainly not more than 2D, because I had at most 2D plus 1 altogether. So this is not the end of the story. What I do next is a very simple move. I don't know if I explain it. This is the picture that I have, and so then I move this guy to this point, and then I have this is and what you do is the following. Here there are at most 2D vectors. You take any linear dependence among these vectors and add it to the existing function here, so that somebody gets some coefficients become 0 and some coefficients between 1. So you just use the previous argument, adding linear dependence on this set to the existing function, and then either a new 1 appears somewhere or a new negative 1, new 0 1 appears somewhere here. I don't know which one. And I can continue this one as long as there are D plus 1 elements between 0 and 1, strictly between 0 and 1. So in the end, I get a new set AI plus 1 and a new set DI plus 1. This is a size at most D, and this is an increase by at most D. So this is the end of the construction. I constructed these vectors and just go, and in the end you end up with the original all one linear dependence. So this is the end of the construction, and I want to show you why this is a good thing to have. How am I doing with time? Oh no, right. So what I have here is this is A1, this is A2, this is A3, this is AI plus 1, this is V. Now I want to see the sum of the elements from here to say this point up to AI. So what is the sum of the element from in V in AIV? So this is nothing else but the sum of V in V alpha IV V, because, but then I have to take away the ones that are in DI that are between 0 and 1. This is alpha IV times V. But this part here is 0 because it is a linear dependence. So this is equal to this quantity here. And then this quantity, the norm is, or the norm of this sum is the same as the norm of this one. Every vector here has norm at most 1. So the norm of this one is at most the sum of the coefficients here, which are all non-negative. And this is definitely smaller than D, because there are D numbers here, all of them between 0 and 1. So this is smaller than D. So the outcome is that every sum from 1 to AI is smaller than dimension. And I am in business now, because if I want to compute a sum from here to some point here, then this differs from either this one or by this one by at most D half elements. So this, because the difference between these two is at most D. So that means that the distance to here, the sum of the vectors here is at most D, and I have to add at most D half, or the sum of the elements from here to here is at most D, and have to subtract at most D half of them. So this is how I get 1.5 D. So this is the better proof, which gives a much better bound than the previous one. And not only a much better bound, but it also gives you a bound which is valid for every norm. I have not touched the norm during the proof unless at this spot here, where I use the fact that each V is smaller than 1 in norm. So this is a strong statement, because it works without any condition on the norm. So this, I want to tell you, there is an even better proof by Greenberg and Sebastiano that you can find in MathSciNet. There is an ordering so that every partial sum is smaller than D, not 1.5 D, but D. So this is a beautiful little proof, but I don't have time to explain it. But I want, so this is valid for every norm D, but of course for some cases you can write a smaller number here, hopefully. Call it S of B, call it the smallest number that you can write here. So SB is the smallest number, such that no matter how a set of unit vectors in a norm B is given to you whose sum is equal to 0, there is a reordering of the element along which every partial sum is smaller than or equal to S of B. So S of B is the Steinitz constant of the norm, or summation constant of the norm. This bound is not so bad, because for the L1 norm, the Steinitz constant is at least D over 2. Or you can prove that, yeah. But for the L2 norm, the existing lower bound is square root of D plus 3 over 2. And for the maximum norm, this is square root of D over 4. So the order of magnitude is square root of D in these two cases here. Questions, which is looks very difficult. That is this the Steinitz constant of the Euclidean norm is smaller than square root of D, or 100 times square root of D, and same for the maximum norm. Even more annoyingly, there is no norm for which the Steinitz constants would be known to be smaller than D over 10. So even in this case, we don't know if the Steinitz constant is smaller than D over 10. So this is a difficult problem. Let me move on a little. And yeah, this is the infinite version of Steinitz theorem I'm not doing too well with time, so I just jump over this one and go to the main application of this theorem. The main application comes from a result of Riemann from 1980 something, which he observed that a conditionally convergent series can be made to converge to any real number by simply rearranging the elements. So if you have a series of real numbers and you look at the set of numbers to which it can be made to converge by rearrangement, then you either get the empty set when the series is not convergent, or you get a single real number when, in the case when the series is convergent, or you get every single real number on the line. And Riemann asked what happens if you have a series of vectors in d-dimensional space. And this was answered by Steinitz with this theorem with this vector sum theorem. It turns out that this set of vectors to which a series of d-dimensional vectors can be made to converge by rearrangement is always an affine subspace. So either the empty set or a single point or a line, etc. Actually, Levy proved the same thing slightly earlier, but only for the two-dimensional case. So this is a famous first application, famous application. This is what started the question, and the proof, which you can find quite easily, is based on the tube lemma, which is the following: if V is a finite set of vectors in a unit ball, and their sum is equal to A, then there is an ordering of the vectors of V, V1, Vn, such that each partial, the partial sum from 1 to k differs from k over n times A by at most 2d. So this is a very simple statement, and you can prove it yourself. Here is a picture. Here is the origin. Here is A, and then you can the vectors go from 0 to A, somehow sum up to A, but you can change this ordering so that all the vectors run here in this tube. And actually the kth partial sum is close to the k over n times A, so the corresponding point on the segment. So this is the tube lemma, and I may return to that one. Another application is a beautiful application in scheduling theory that I want to explain next. The flow shop consists of m machines, 1, 2, etc. m, and n jobs, 1, 2, etc. n. And each job is to visit each machine once and no interruption, and the ith job takes Tij time on the J machine to execute. So to give you an example, you have a piece of wood that you have to cut into two by a saw, and then you have to drill 2 holes in each piece, and then you have to put it, you have to polish it, and then you have to paint it. So there are 4 machines. This is cutting, this is drilling, this is polishing, and this is painting. And you take the first job. This is shown here with blue, and it takes up this time, and then you can start the same job on the second machine, and the same job on the third machine, and the same job on the fourth machine, and then comes the second job. You can start it exactly here. It lasts this long, but you can't start its continuation because the machine is occupied. You have to start here. Then it finishes here, so you can't start here because it's still on the previous machine. So you have to start here. You have to start here. So what you have is you see the green job running through the machines, and here is the ith job going through the machines in this order. And of course, the target is to minimize the final execution time when all the jobs are finished on every single machine. And it is also required that the jobs go through these machines in this order. So first machine, second machine, etc. This problem is NP complete, so there is no hope of a general case algorithm, but I'm going to give you a schedule which is very close to optimal, and I show you what under what conditions. So assume that the maximum of the execution times is C. And write Tj for the total execution times on the jth machine. And let Tmax be the maximum of the total execution times on the jth machine. And of course, Tmax is smaller than T final because that's inevitable. Now, the statement is that there is a schedule so that the final execution time is smaller than the maximum execution times M times M minus 1 times C, which is just, hang on a minute, I have to check if I don't lose electricity. Yeah, I lose electricity in some machine, so I have to plug it in. But I am all yours otherwise. Just hang on a minute. So there is a schedule whose final execution time is not much worse than the maximum times the number of machines times number of machines minus 1 times the maximal execution time. And what you do is you find a Tij tilde between Tij and C such that the sum of the Tij tildes is equal to Tmax on everybody or every machine, which is you can simply add dummy jobs, and they will take up some time or some slots on your schedule, but they don't do any harm. They simply are not executed. And then once you've done this one, you define a vector v sub I associated with the ith job. This is the job I, and you associate it with Ti1 tilde minus Ti2 tilde, Ti2 tilde minus Ti3 tilde, etc. This is an M minus 1 dimensional vector. By the construction, the sum of the vectors is 0, because every execution time on every machine is the same. And every vector in here is C times the maximum is a vector in M minus 1 dimensional space with maximum norm at most C because of this condition over here. So very good. Then by Steinitz, there is an ordering V1 etc. Vn such that from 1 to k Vi is smaller than dimension, which is M minus 1 times C, because we inherited C from the definition, which means that the sum of the execution, I just dropped the tilde from T on top of tilde, from 1 to k Tij, 1 to k j plus 1 is smaller than M minus 1 times C. So this is when the kth machine finishes in the first machine. This is when it finishes on the second machine. This is when it finishes on the, this is the sum of the vector, not when finishes, sorry. So this is the sum of the vectors here, the sum of the vectors here, etc. Now, I see that this difference is not too big. This is what it means. This test is not too big in either case. But unfortunately, they can overlap. So how can we avoid overlapping? Because the jobs must not overlap. So I leave the first row intact. In the second row, I add m times c to every single starting execution. Then I push this one up by m times c. So this one moves up, and on the second level or the third machine, I push up everybody by 2m times c. So it is here and on etc. So I push up every one of them one by one. So let's see. So the job K finishes on machine J is sum of Tij plus K minus 1 times M times C, because this is how much I added. And this is smaller than or equal to I equals 1 to K Tij plus 1 times K minus 1 times M times C, it is here, it's written here, plus M minus 1 times C, which is what I added over there. And then if you look at it, this is when job K starts on machine J plus 1. So job K finishes on machine J before it can start on machine J plus 1, and this is a valid schedule. And so this is what I wanted to prove. I want to mention there are many more such applications in scheduling theory, but I can't explain them all. So let's move on. Integer programming, and I have 15 more minutes or so. No, I just jump over integer programming and move to another topic. This is sign sequences.
Professor Imre, excuse me. In your previous explanation, if one applies the simplex method, the linear programming, it gives the same answer, the answer you come up with.
I'll tell you what it gives you. That so here is an integer programming problem. Maximize this quantity subject to an equation, and Z should be an integer, and A is an integer matrix, C is an integer, B is an integer. And this is again an NP complete problem.
NP.
But assuming, question?
Yeah. Please explain.
Assuming that Aij are smaller than or equal to delta in absolute value, you can you want to see whether this problem is feasible, and there is a sort of polynomial time algorithm to check whether it is feasible. Polynomiality is in this delta, which is in general you can't assume that the coefficients are small. So if you assume that the coefficients are not too big, then Stein's theorem can be applied and used to show the existence of a fairly good algorithm. This is again a new invention 5 years ago, and there are many offsprings from it, many further results in this direction. Now I move to sign sequences, if you let me. So in this case, there is a different setting. I have a sequence of vectors in the unit ball, v1, v2, vn. Actually, it can be infinite, I don't mind either. And what I want to find is signs epsilon 1, epsilon 2, epsilon n, plus 1 or minus 1, such that the sum of these vectors up to from the first to the k with these weights plus or minus 1 is bounded for every single k. For every k. And as is similar to the previous one, but here previously I could change the order of the vectors, and here I cannot change the order of the vectors, but I can give signs to the vectors and keep them small. And here is an old theorem of myself with Greenberg, saying that there are signs epsilon 1, epsilon 2, epsilon n, so that the maximum of this of the partial sums with this ways is smaller than 2d minus 1. Again, just dimension, it depends only on dimension. So if you wish S as be the sign sequence constant of the given norm B, which is the smallest constant that you can write over here. So the meaning is that no matter what vector system you give with these conditions, there are signs so that this one is smaller than SS of B. And I want to give a quick indication of how the proof goes. It is again linear dependencies. So it's again a construction. V of k is the vectors from 1 to k plus d. And I give a linear dependence from vk to minus 1, 1, this interval. Linear dependence, V is missing here, sorry. V is, so this is a linear dependence, and I have to specify again. Wk is the set of vectors for which this linear dependent coefficient is between strictly minus 1 and 1. And I claim this is going to be smaller than a size or a set of size smaller than d. And if beta of k, if v is not in this set between minus 1 and 1, but the beta of v is plus or minus 1, then beta k plus 1 is also the same number, k plus 1 or minus 1. So you keep the sign. Once you reach plus or minus 1, it will stay plus or minus 1, and you change afterwards. So k equals 0, beta 0 is absolutely 0 is okay, because then the number of coefficients between 0, strictly minus 1, 1 is at most d, everything is okay. From k to k plus 1, what do you from k to k plus 1? So here is my beta k dependence. This is beta k. This is the last element. Now I add to this linear dependence the vk plus d plus 1 element with weight 0. Then I get a new linear dependence on vk plus 1, one more element added, and there are d plus 1 coefficients strictly between 0, minus 1 and 1. You can again add the linear dependence with a suitable multiplier so that one coefficient is kicked out to z plus 1 or minus 1. This is going to be your beta k plus 1. So this is the same argument as before, just a different setting. And then you said epsilon I equals beta k v sub I if beta k v sub I becomes 1 or minus 1 along the way. In the remaining at most d vectors, epsilon I is undecided, and you can choose any number you want. And now I want to show why is this so good. So if you add the vectors from 1 to, if k is smaller than d, then there is no problem, because this sum here is smaller than the sum of the epsilon i's, which is k, which is smaller than d, so this is fine. So when k is larger than d, then I write it as k plus d, and I look at the sum of the vectors epsilon I vi from 1 to k plus d. So this is the same as the sum of epsilon v in vk, right? Whenever epsilon is plus or minus 1, this is the same, but I have to take away the linear dependence on this is wk, on wk. So then this is, because this is 0 here, this is going to be, so no, sorry, wrong. This is 0 here. So the difference is exactly on wk, and epsilon v minus beta k, v times v. This difference is at most 2 in absolute value. This difference here. So the norm of this one is smaller than if I add 2 on every element of wk, which is at most 2d. So I promised you 2d minus 1, and I leave it to you to check how the minus 1 can be put in there. Any question? Again, the sign sequence constants of L1 norm is d. The sign sequence of constant of the Euclidean, the maximum is larger than c times square root of d. You can easily find examples showing that. So the question is whether this is smaller than OD and smaller than OD, or square root of d. But even little of d is not known in either case. Now let me see how I'm going. No, I'm not going to this part, but I want to show you something. The Chobanian's transference theorem from 1994. This is a beautiful result. It says that for a symmetric norm with unit ball B, the Steinitz constant is smaller than the sign sequence constant. The summation constant of the norm is smaller than the sign sequence constant of the norm. So this is a very useful result and has been used many times and will be used many times and will give rise to further transference theorems of this type, which means that the sign sequence constant is easier than the summation constant. Whenever you have a proof of this one, you have a proof of this one. But when you have a proof of this one, you may not have a proof for the other one. Here is the proof of Chobanian's theorem, and this is going to be my last slide. So consider the subset V of the unit ball with n elements whose sum is 0, for which the summation constant is reached. So S of B is attained on this set V, which means that there is an ordering, namely V1, V, etc., Vn, so that the sign sequence constant is equal to the maximum of all the partial sums along this ordering. But for any other ordering of V, there is some partial sum that is at least SB. So this is the setting for my proof. And now I let the sign sequence act on this sequence. So let epsilon n plus minus 1 be the best sign sequence constant for the V1, V2, etc., Vn sequence, which means that the maximum over k from 1 to k epsilon IV is smaller than SSB, because SSB is the maximum. So this is, now comes the change of the project. So here is V1, V2, V3, etc. And here are the signs. Plus 1, minus 1, minus 1, plus 1, minus 1, plus 1, etc. This is just an example. Plus 1, minus, plus, minus, plus. Now I create a new ordering out of this sign sequences. I put V1 here because it has a plus sign. I put V2 here as the second vector because it has a plus sign. I put V5 here in the third position because it has a plus sign and I get negative coefficient. I put a V7 over here because it had a plus sign and this one had a negative sign. On the other hand, I see this is the first, V3 is the third. V3 is the third. This is not here. V3 is the third vector, which with the first vector which has negative coefficient. I start from the other side. V4 is the other one, which is V4 is the other one, which is negative. I put here over here. V6 is the next one, which is negative. So the plus sign vectors come in this order, and negative sign sign vector come in this order. And somewhere it ends up with V sub n, because this is the last used either with plus or minus size, I don't know. This is a new ordering. Now I want to see the sum of the vectors from 1 to vk, assuming that vk is in the positive region. So I want to estimate v1, v2, v5 as a vk, the positive elements up to k. So this is the same as all the elements up to k, plus epsilon I times all the elements up to k, because if epsilon is positive, then this is 2 times vi. If epsilon is negative, then this disappears completely. So if I divide by 2, I get this for this sum. So I know that the norm of this sum here is smaller than, because this is smaller than S of B, this is smaller than SS of B, this is smaller than 1/5 times SB plus SSB. Are you with me? And in the other direction, this is, if I take a sum which goes to the negative region, then this is the same as going from here to the end, because the sum of the vectors is 0. So this is negative times sum of this one, and you get an identical expression for those vectors, negative 1, 1/2 times vi, etc. So what you get is this, that this sum is smaller than 1/2 times SB plus SSB. Very good. So we have this sum is smaller than this one, and this sum is always smaller than this one. But because this is a different partial sum, one of the partial sums has to be larger than S of B. So this quantity here is larger than S of B, which means that S of B is smaller than SS of B. This is the proof of Chobanian's transference theorem. I have to stop here. So I stop with a question: Is there opposite inequality in the opposite direction? Say SS of B is smaller than 4 times S of B. I have no clue. Of course, here you can always write D, because the vectors are at most D in each case, but that's not so interesting. So you need a constant here. 100 would be equally good. So this is where I stop. Thanks for your attention.
Thank you, Professor Imre. It was a wonderful talk with lots of elaboration, unlike usual seminars where you included the proofs, and which were really, really very interesting. Thank you. Are there any questions from the audience side? Please, you can drop your question in the chat box, or you can unmute yourself in order to share your views or any question. Professor Imre, I was just curious about one particular aspect about so all these problems, because I joined a bit late.
Yes.
So I skipped the first half of your lecture. So everything is related with the ordering of the vectors, right?
Yes.
And
yes, the first.
Yeah, and I was just curious about the selection of those particular vectors. So initially, you select the vector which are dependent, linearly dependent, sometime, or independent.
So you have many vectors, and any D plus one of them are linearly dependent. But other than that, you can't, and you don't have to assume anything.
And
so if with linearly dependent, then you are in a smaller dimensional subspace, and then you get a slightly better bound. So this was my original theorem. Here, this is what I show you on the screen.
Okay, and this partial sum restriction is giving a kind of a smell of the Catalan number, the pattern of the parenthesis or the moment that you need to order them in a way that it does make sense.
So you can think of this one if you have many vectors that sum to 0 in the plane, right?
Okay.
Then you can order these vectors by slope.
Ah,
And
okay.
if you add them together along the slope, you get a, let me make a picture here. This is the origin. Then you start this way, this way, this way, this way. You get a large convex set.
Ah, okay, okay, okay.
Every partial sum is, I mean, some partial sums go far away. The question is whether you can find a much better ordering. Namely, you want to keep this whole polygonal path in a ball of radius r, radius m. And then the answer is this one goes out normally far away. But there is another ordering for which everybody stays within a ball of radius atmos dimension. So this is the main idea. This is the main question in the whole story.
Who started this question? It's a wonderful question.
The question came from Riemann,
Riemann.
and people understood quickly that this is what is needed. This vector sum theorem is needed. What goes under the name of Stein's lemma nowadays.
And it helps in improving the simplex method in teacher programming.
It has uses in many areas of mathematics, including integer programming, as I tried to explain, including many other fields. So there is a booklet with 200 citations connected to vector sum and sine sequence problems from 1982 probably. And since then there have been many more papers, and you type in Stein's lemma applications and you will find various and beautiful ones. I did not have time to explain them all.
Okay, but anyways, the motivation you built through this particular presentation is already too overwhelming, and the results are strikingly beautiful. And thank you very much for accepting our invitation, and we will love to have you sometime around in the same seminar in the John Conway. Do you have some memories with John Conway to share?
Yeah.
Did you meet him?
Yes, I met him once or twice, and I listened to, we were introduced to each other, but I never talked to him proper. But I listened to a few of his talks, and and it was a pleasure to listen to him.
Yeah,
he was an
thank you.
speaker.
Thank you, Professor. Thank you, everyone.
Thank you very much, and goodbye to everybody.
Goodbye.